All right, so welcome to my series of video on statistics. And in this final video, I've labeled it a tutorial video on correlation and regression. All right, so in this video, it's a tutorial video where I have used a regression output to go over the concepts of regression. Now, the question says that research was conducted to examine factors that could influence the performance of students in a statistics quiz. Some of the factors explored in the model include the number of hours spent on studying, income level per week, intelligence quotients, and gender. Below are the results obtained from the statistical test conducted on a sample of 50 students. So up here, we have the correlation matrix, where it shows the correlation between the variables. So HRS and quiz, there's the correlation. Income and HRS, there's the correlation, and on and on and on, all right? But we are more, so this is not necessary now, this output, we are more interested in the regression output. So in the regression output, our multiple R is here. Our R square is absent. And I'll show you how to get it later. Our adjusted R square is here. Our standard error. So this is the standard error of the whole regression equation. That was what I was talking about earlier. It's called standard error of estimate. All right. Everything is given in the equation. The number of observations are 50. So this is the ANOVA table. Now, this ANOVA table here, is actually the F test. So this ANOVA table here is actually the F test. Okay. This ANOVA table here is actually the F test. All right. And the F test is used to check whether the R square is significant or not. So this ANOVA table here is the F test table or the F statistics table. And the purpose of the F statistics, as I've said in the teaching video, is that it is used to assess whether the R square is significant. Put in other words, it is used to assess the overall significance of the model. So in other words, it is used to assess the overall significance of the model. So in other words, it is used to assess the overall significance of the model. That's the purpose of the F test or the ANOVA test there. All right, that is the purpose. Then when you come down here, we have the actual. When you come down here, we have the actual regression estimates here. When we come down here, we have the actual regression estimate. So when we come down here, we have the actual regression estimate. Now, in that regression estimate, we can see that there are some variables missing, okay? At this level, don't worry yourself about how to compute the p-value. Don't worry yourself about that, okay? We can compute the probability value reading tables, but don't worry yourself about that, okay? Don't worry, but you must know the relationship between coefficient, standard error, and then t-statistics. And let me show you. Remember that when we are computing t-statistics, remember that a t was equal to the estimated beta minus the actual beta divided by standard error of the beta. Remember that, okay? And always based on the hypothesis, the hypothesized beta is equal to 0. Always based on the standard hypothesis, the hypothesized beta is equal to 0. So what that means is that it will be t is equal to beta 1 minus 0 all over standard error of beta 1. And that will give us beta 1 over standard error of what? Beta 1. So in other words, all that I'm saying is that t statistics is the beta divided by standard error of that beta. That is how we get the t statistics. It is the beta divided by the standard error of the beta. That's how come we get the t statistics, okay? And then if you do change of subject, the beta 1 therefore will be equal to the t times standard error. So anytime you multiply the t value by the standard error of the beta, we get the beta itself. And also, if you do change of subject again, standard error of beta 1 is equal to beta 1 itself over the t. That's another relationship. So this is the first relationship, this is the second one, this is the third one. All of them are gotten through change of subject, all right? All of them are gotten through change of subject, okay? All right, so let's fill the table up now. We don't have our R square. Remember, we don't have our R square, all right? And by formula, remember that R square is equal to sum of square regression over total sum of square. This is R square. R square is sum of square regression over total sum of square. So let's go and identify it from the table. From the table, we identify it from the ANOVA or the F statistics table. All right. So in this table, you see we have residual, then we have SS. Okay. SS. So this is sum of squared. So SSR. So here, the regression thing here, this figure here, is sum of squared, but it is for the regression. So sum of square regression is 106.51. Or let me round it to 52. Okay, so sum of squared regression is 106.52. Then sum of squared residual error is 1723.10. 1723.10. 1723.10. So this is the sum of squared residual error. So if you want to get the total sum of squared, you just add these two. Remember, total sum of squared is sum of squared regression plus sum of squared residual error. So it is 106.52 plus 1723.1. So that will give us 1829.62. All right. So that is the total sum of squared. So if you want to find the R squared, it is sum of square regression 106.52 divided by the total sum of square of 1829.62. Okay, so when we divide 106.52 by 1829.62, our R square will be 0.058. Or in terms of percentage, so sometimes in the question they can give you R square and they will still say compute R square when they say that they want you to make it in percentage. So in terms of percentage, R square is 5.8%. All right. So there's the interpretation. The interpretation of the R square is that 5.8% variation in Y. In the question, what is the dependent variable? Let me check. The dependent variable in the question, the dependent variable is we are looking at factors that influence performance. So performance is the dependent variable, right? So a 5.8% variation in performance can be explained by its relationship with the independent variables. .8% variation in performance or in the dependent variable can be explained by its relationship with the independent variables, right? That's how we interpret the R square. Now, we may also want to test whether this R square, this 5.8, whether it is significant or not. So we want to test the significance of the R square. Remember, we are going to use the F test, okay? So R square is equal to 0, that's the null. And the alternative is that R square is not equal to 0. So although we have an R square figure of 5.8, maybe statistically, it may not be correct or it may not be significant. That's why we need to test its statistical significance. So that is why we do the hypothesis testing, okay? Now, we use the F test to test this. F test to test the overall significance of the model. Or the significance of the R square. Now, let me show you something. Why is testing overall significance of the model synonymous to testing the significance of the R square? Let's look at something. R square is the percentage variation in the dependent variable that can be explained with its relationship with the independent variables, okay? So if your R square is 0, if your R square is insignificant, or statistically, if your R square is 0, it means that the dependent variable has no relationship with the independent variables. It means that the dependent variable on the overall, it has no relationship with the independent variables, okay? Which means that overall, your model is not significant. The whole regression model on the overall, it is not good. It is not significant. Because once your dependent variable has no relationship with the independent variables, it means that the independent variables significantly can affect the dependent. All right. Okay, so that's why we also call it a test to test the overall significance of the model. Now, let's conduct the F test. At your level, nobody will ask you to go and read F test table. You just have to read or know the p-value of the F test. So normally in the regression equation or in the ANOVA table, that's the last thing you see on your right. This is the p-value of the F test, this one. The last item is the p-value of the F test, the probability value of the F test. The actual F test figure will be here. I think it has been omitted, but don't worry on how to compute. It's not necessary now. Okay, there's a formula to compute F, like it's here. If you read some statistical books, there's a formula to compute it. It's the figure here divided by the figure here, but it's not necessary now. But all I want you to know is that the final figure in the table here to your right is the p-value of the F test. Okay, the actual F test we may not need it, but you can use the p-value approach of the F test. So once the p-value, so here you just say that since the p-value is equal to 0.5999, right? The p-value of the F test was, let me check, 0.5991, sorry. Okay, it is greater than alpha of 0.05. Remember that when it comes to p-value, if it is greater, we fail to reject. I taught this in the hypothesis test video. Just check. When your p-value is greater than your alpha, you fail to reject. But when the p-value is less than the alpha, we reject. Okay. Because if you are going to draw this, anything so here 0.025, 0.025. So anything more than 0.025 will come into the acceptance region. So that's why we accept. So it is greater than 0.05. Therefore, we fail to reject, which is the same as saying accept. So we fail to reject the null hypothesis and conclude that R square is not significant. And conclude that the R square is not, because if we have failed to reject this null, it means that indeed the R square is not significant or it is 0. Okay, so that would be our conclusion from the F test, right? That will be our conclusion from the F test. Okay. All right. Now let's come to the coefficient table itself. So here, what we are going to do is that we are going to fill up the table, all right? So you see, there is no standard error for HRS. There is no standard error for HRS. And I've told you that beta coefficient here divided by standard error, you get your T. So you can try it. The beta coefficient, this figure, divided by this figure, you are going to get this figure, right? You can just try it. That means that if you also multiply the T by standard error, you get the beta. You can try it. And if you want to get standard error, you just also divide the beta coefficient here by the T, you get a standard error. So if you want to fill the table, the standard error for HRS will be the beta of negative 0.237 divided by a standard error of negative 0.517. I'm just trying to, I'm trying to round them, like round it. So if you compute this, you pick a calculator and you punch negative 0.237 divided by negative 0.517. The standard error you get is 0.4584139. So that will be the standard error here. You get 0.4584139. All right. So that'll be the standard error here. Then again, we can compute the beta for IQ. Remember, I said that beta by the formula is standard error times T. So the beta coefficient for IQ here will be the standard error times the T. All right, so when we multiply the standard error by the T, so we are going to multiply 0.2431. I'm rounding it, 0.2431 by 0.9530. You're going to get a beta of 0.231673. So the beta here will be 0.2316. So let me write it. So beta for IQ will be 0.231673, of course. So of course, if your T is negative, you would have gotten a negative beta, right? If your T was negative, like here, since the T is negative here, you see the beta is also negative, right? As for the p-value, don't worry about it because this one, it would involve complex table reading. Okay, but it is omitted because we just want you to know that P can also, the probability can be found, but it's not relevant now, right? It will involve complex Excel analysis, but just know that it can be found. Okay. So let's wrap up. Fill in the missing spaces. We are done with that. We are done with almost filling every missing space. The next one is specify the estimable regression equation. Okay. 2, specify the estimable regression equation. Now, estimable regression equation simply means write a regression equation that we are yet to estimate. All right, we are yet to estimate. Let's assume that we have not estimated and we don't know the beta values. So we are yet to estimate that regression equation. That's what we mean by estimable. Okay, when you are yet to estimate the regression equation, we call it estimable. That means that you write them in their functional form. Okay, you are going to write it in the functional form. So remember, the dependent variable was performance, right? So we have performance is equal to the intercept beta naught plus one of the independent variables was HRS. So beta 1 HRS plus another independent variable was income. So beta 2 income. Another independent variable was IQ. So plus beta 3 IQ. Another independent variable was gender. So plus beta 4 gender. And of course, you bring your error term. Okay, you bring your error term. So that's what we mean by estimable regression equation. Estimable regression equation means that write a regression equation of the intercepts, HRS, income, blah, 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 as well as the dependent variable, but don't put in the coefficient. Just write them beta, 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 right? So that's the estimable regression equation. Then, 3, what percentage variation in Q-score can be explained by the variation in the independent variable? So question 3 was asking about R-square, and we have done that already. All right, it was asking about R-square. Just refer to your notes. The R-square was 5.8. So it means that 5.8% variation in the Q-score can be explained by its relationship with the independent variables. So question 3 was just asking about interpreting the R-square, which we have already done. Question 4 was on commenting on the overall significance of the model. So question 4 was commenting on the overall significance of the model. So the overall significance of the model is just to do the F test or the ANOVA test, the F or the ANOVA test, to check whether the R-square is significant, which I've also spoken about it already. Okay, so it looks like we ran ahead of ourselves. So this is the test to check the overall significance of the model. You check whether the R-square is 0 or not, that hypothesis. Then you use the p-value of the F test. So if the p-value of the F test is more than 0.05, you fail to reject and conclude that the R-square is equal to 0, it is not significant. That means that on the overall, the model is not significant. On the overall, the model is not significant, all right? So let's wrap up. So the subsequent question is about correlation. I'm teaching regression. I'll do a correlation video as well, but for now, let's ignore question 5, 6, and 7 because they are on correlations, right? But let me add a little bit to this, even this regression question. Let me add a little bit. Now you can also be asked to find, so this is the estimable. You can also be asked to find the estimated equation. So estimated equation simply means that you write all the betas, whether they are significant or not. So you are going to look at them and write it. So the beta for the intercept was 12 point something. That for HRS was negative 0.23, blah, blah, blah. Income was this. IQ, we found it on our own. And then there is gender. So you are going to write them, right? You are going to write them. So as I always do, because of the space, I'll just round the figures, right? I'll round the figures. So the intercept was 12.06, blah, blah, blah. So it will be 12.064. Then HRS, is beta coefficient was negative 0.237, so minus 0.237 HRS. Then for income, is beta was minus 0.006 income. Then IQ, we computed the beta was positive 0.2317 IQ. Then for gender, is beta was so minus 1.646 gender. Okay, so this is the estimated equation. Then we bring the cap. Then you can also be asked to find final equation. Now, when you are being asked to write the final equation for a regression, okay, when you are being asked to write the final regression equation for regression, you write only the significant ones, okay? Significant one means that the t-value of that beta is more than 2. So let's go and check. When it comes to intercept, 3.8 absolutely is greater than 2. So the intercept is significant. Absolute 3.8 is greater than 2. So the intercept is significant. HRS absolutely is 0.51, which is less than 2. It means HRS is not significant. Ignoring negatives, absolute t-value of HRS is less than 2. It means that HRS is not significant. Okay. Absolute t-value of income, when we ignore negative, absolute t-value of 0.934 is also less than 2. It means it is not significant. IQ 0.95 is also less than 2. It's not significant. And then for gender, absolute in terms of 0.9038 is also less than 2. So it means that all the things here are not significant except what? The intercept. So when it comes like that, and you are writing the final equation to be performance is equal to this one, the intercept, which is the significant one, which is 12.064. On the assumption HRS was significant, it would have been minus 0.237 HRS. Okay. But once all the things here are not significant, only the intercept that will come in the final equation. All right. Okay. So you can try your hands on more examples. So let's round up. When it comes to P, let me say this again. When P value is less than alpha, we reject the null hypothesis. When P value is greater than alpha, we fail to reject the null hypothesis, right? That's for P. When it comes to T value or even Z value, when the Z value absolute is greater than 2 or any critical T, okay, we reject the null hypothesis. I've done this so many times using the graphs, so you should know this by now. Then when the absolute T value is less than 2 or any critical T, we use 2 only for regression, because regression sometimes data point is many, and you can't read any degree of freedom anywhere, right? Or any critical value, which can be read, we fail to reject H naught, okay? So by ending, anytime your T value is more than 2, your P value in terms of probability will be less than 0.05. By so that it can yield the same conclusion. So anytime the T is more than 2, reject. There is no way you get a P value more than 0.05. It can't happen. Once your T is more than 2, your P value will be less than 0.05. That is the norm. All right. So in a question 2, instead of using T statistics to conclude on whether the B tests are significant or not, you can use the P. But for the P, when you're using P, the thing is insignificant when the P is more than 0.05. So unfortunately, we don't have the P values here, but let's even look at that for income. Income, the P is 0.35, which is more than 0.05. So income, the coefficient here is insignificant, right? The same applies to gender. When it comes to the intercept, the P is far less than 0.05. That is why the intercept is what's significant. So in conclusion, you can either use the T values or the P values to check the significance of the coefficient. And that can help you write your final regression equation, right? It has been an interesting time being with you. And this will bring me to the end of the series on statistics, because regression is the final topic. And like, comment, share, and most importantly, subscribe. All right. Thank you for patronizing the content. Thank you.